And then in the next line, what I did was, this is I sub t. I sub t is this difference there between I of xy at t plus 1 minus I of xy at t. Well, what is I sub t? Well, if I of x is the derivative of I in the x direction, and I sub y is the derivative of I in the y direction, I sub t is the derivative of I in the time direction. It's what's called the temporal derivative. And remember, our imagery is now a function of x, y, and t. So I can take a derivative in x, in y, or in t. Another way to think about it is, if I just look at some point x, y, and I see how much the image changes from t to t plus 1, that's my temporal derivative. And then finally, on this last one, you'll see that this here is just ix times u plus iy times v. That's just the gradient, ix, iy, dotted with however the point is moving. That's uv. So we write that like this, that 0 is approximately it plus the gradient of the image dotted with this vector uv. uv is the direction of motion. Got it? Cool. All right, keep going. Now, this is approximation in the limit as u and v approach 0. Now, you might ask, how can u and v approach 0? Well, the idea is that in the limit, of course, if t was very small, the amount of motion you'd get would be very small. You would just have the direction. So we're going to assume that they're very small, and we're just going to take this equation directly as is, that 0 is equal to it plus this gradient, and that, written out either above as a gradient or here in algebraic form, that's the brightness constancy constraint equation. Say that 5 times fast. Brightness constancy constraint equation. All right, ixu plus iyv plus it equals 0. So here I have the equation written, and I've written it both ways, just the original, the way using the gradient imagery dot product way, or in the algebraic way. Question: how many unknowns and how many equations per pixel? The number of unknowns is easy. What was I trying to solve for? U and V, right? U and V is which way is this point moving? Great. How many equations? Well, yes, there are 2 equations up there, but they're the same equation. I have 2 unknowns, but only 1 equation per pixel. This should bother you, right? It's very hard to solve things that you've got twice as many unknowns as you have equations. Because remember, I have a different U and V possibly for every pixel. So I've got 2 times the number of pixels unknowns, and I've got 1 equation per pixel, 2 times the number of pixels. What's going on here? So intuitively, we can think about what this constraint means as follows. The component of uv that's in the direction of the gradient, that's what we can measure, right? That amount will tell us how much the image will change. That's why that's the amount of it, I sub t, the derivative, right? So what this is saying is, if this is the direction of our gradient, as indicated here, right? Here, suppose this is my real uv right there. Well, any other uv that has a component of the same amount in the direction, but I've got a u prime v prime, that's in an extra component that's parallel to the edge, all right? And this new vector here, which was the original u v plus u prime v prime, it has the same amount perpendicular to the edge in the direction of the gradient, but a different amount along the edge. Remember when we were doing corner finding and we put up the thing and we said, well, if you slide it up and down, if your little patch is on the edge of the black square, if we slide it up and down, we can't tell at all. We can only tell how much is being moved perpendicular to the edge. That's what's going on here. Locally, we can only tell the amount of motion that is perpendicular to the edge in a little area. When you think about this little area, you can think of it like looking through a little hole. Remember from our talk about cameras that's called an aperture? And this general problem, this is called the aperture problem. So here is a very interesting line drawing. It's a line with 2 parts. And notice it has a corner. And here's the next one. Voila, it moved. Back, forth, back, forth. I can do this all day. Okay? And you can see it moving. Okay? Great. Let me put an aperture over that. So here is a great big green aperture. All right? And now I'm going to move that line thing the same way. And now it goes like this. Whoa. Now it's moving up. Or at least it feels like it's moving up. Is it moving up? No. In fact, here I've made it transparent. Okay? So now, this is the same motion, right? In fact, if you look at the corner, you can tell this thing is moving over and down a little bit. But if you were to look just inside the circle, it looks like it's moving up, not down and over. That's the aperture problem. Okay? You can only tell the motion locally in the direction perpendicular to the edge. There are some other effects of getting sort of strong gradient flow. So this is a single pattern. And then I'm going to use PowerPoint to just put this in motion using animation. So there's no video going on here. This thing is just moving back and forth. And hopefully, as you see this move, every time it bumps, you're going to see the inside move relative to the surround. It's not actually moving. That's in your head. And that's because of various noise and various ways of computing the gradient. More details, and it's not just the aperture problem, but it's showing the sensitivity in your mind, in your head, of the gradient. The aperture problem also is sometimes used to explain the barber pole illusion, right? So it's spinning around, but you see stripes going up. And in fact, in the you shouldn't believe everything you see on the web universe, some people will say that the aperture problem explains the barber pole illusion. But actually, that's not really true. It has to do with it. It doesn't explain it. Because if you think about it, the gradients here are not quite vertical, right? They are off a little bit. And so you can get a flow that's like that. And you have to do some integration to decide that the whole thing is moving up. And actually, Ellen Hildreth, a very long time ago, in her PhD thesis, looked at how you use the normal flow and you can integrate it in order to make you might see the pole move up. But it is the case that there are places out there that will tell you that this is because of the vectors.
Let's say we have a bright edge that we can see at time t. The same edge at time t plus 1 has clearly moved to the right. Now when analyzing the optical flow here, you might think, what aperture? Is there a magical green donut that is forcing you to look at small parts of the image at a time? Well, no. It's because with the brightness constancy equation, we're trying to analyze each pixel at a time. We look at the image intensity at that specific location xy, how that changes from time t to t plus 1, the horizontal and vertical image gradients, again at that specific location, and we try to compute the displacement uv for that particular pixel. Since there is no actual aperture limiting your view, how would you improve this approach to get the correct optical flow? Think about what additional constraints you might be able to use. For instance, do you think nearby pixels move together, that is in the same direction and roughly the same amount? And can this be used to optimize our optical flow computation? Similarly, can we say that motion over an entire image should be consistent? Or should we just look at distinct regions, like corners? Select the choices that you think are valid and useful. Anything else? Mark Other and enter it in the box. Yes, nearby pixels tend to move together. This is because an object seen moving in a certain way occupies more than a few pixels. Well, otherwise it would be hard to see. This can be thought of as a local constraint, and we'll see more of this later. Saying that motion must be consistent over an entire image is a pretty bold claim. But it is still fairly valid and useful, especially when used as a soft constraint. This means you're not saying that motion across the image has to be identical. It's just that solutions to the optical flow problem that generate consistent motion are preferable. As you might have guessed, this is a global constraint. Remember that our goal is to compute optical flow at each pixel, that is, dense flow. Now if we consider only distinct regions, then how are we going to do that? Well, at distinct regions like corners, the ambiguity of flow direction is small. If we compute optical flow at these regions, we could interpolate the flow between them. So yes, this is a useful approach as well, although it might result in approximate flow. Anything else you have in mind? Don't agree with these constraints? You know where to discuss.
All right, so we have a problem. The brightness constraint equation gives us more unknowns than equations, more directions to move than we have pixels. How are we going to recover the motion? Obviously, we need some extra constraints. We need some additional constraints. So we'll talk about sort of a global approach now, and the next time we'll talk about a more local approach that actually is used, and in fact, some of you may even implement. Sometime long, long ago in a galaxy nearby, Bertolt Horn and Brian Schunk did some work on what was called smooth optical flows. And basically they said, let's try to come up with an optical flow that minimizes some error. Okay? So the first part of the error is how much do we violate the brightness constancy constraint equation, right? Basically, that middle term right there, that's supposed to be 0, right? IXU plus IYV plus I sub t is equal to 0. So violations of that mean that it's not 0. Sometimes it's positive, sometimes negative. I square it, and I sum it up over the whole image. That would be how bad my flow is with respect to the constraint equation. All right? But we know we can solve that exactly because we have more unknowns than constraints. So if that's our only constraint, we're not done. But we're going to call this the constraint error. By the way, I kept partially, originally I had stolen, then I did it on my own. I kept the integral signs instead of summations because back when this work was done, we'd like to think about images as actually continual functions. Of course, if you were to implement this, you'd actually have to do summations. I will also tell you the fact that summations are not integrals matters. And if you take a look at some of the work that was done in shape from shading, doing it as an integral was actually hard. Doing it as summations was in some sense a little bit easier. But for here, the difference doesn't matter, so I just wrote it as being summed up over the image. So here we have our optic flow constraint term. Now we need another term. Well, it says smooth optical flow. Here's the idea. Remember when we did stereo, the state-of-the-art solution that I showed you that did that beautiful recovery, used a bunch of terms, some that had to do with the data, but it also had to do with the smoothness of the disparity field. That was the idea that surfaces don't change a lot all over the place, but they tend to have a particular depth or vary smoothly. The same could be said of motion. That is, so if I've got something moving around, the motion vectors from one point to the next change slowly. So let me come up with a penalty term that says I really don't like velocity fields where the velocity changes quickly from one location to the neighboring location. So that's shown here. These ux, uy, that's the derivative of u. Remember, u is the x component of the motion field. The derivative in the x direction squared, because it would be positive, negative. Derivative in the y direction squared. Same thing as here, which is v sub x, v sub y, the change of v as you move in x, the change in v as you move in y. Again, everything is squared. So the idea is we would like this thing to be like 0 or as little as possible. By the way, what would it mean for this to be 0? Well, for this to be 0, that would mean that all the u's were constant, right? They were all the same value, so the derivatives would be 0. And all the v's would be constant. So if all my pixels were moving with the same UV, the whole image was moving the same direction, this value would be 0. Any other u's and v's will cause this term to have some value, and we want to try to minimize this thing. So now we have these two terms. We have the constraint equation error term, and we have the smoothness error term called E sub c, E sub s. And what we want to do is we want to find the UV at every pixel, and there's going to be a different UV at every pixel, that minimizes this total error, which is just the smoothness term plus some weighting factor times the constraint term. And the weighting factor is sort of how much you believe your data. So the bigger the weighting factor is, the more important the satisfying the brightness constancy constraint is. The smaller the weighting factor, the more the smoothness term dominates. And what value it should have is a function of sort of how much noise there is and how smooth you believe the entire thing is. So this was part of a general approach, variational approach, where you're going to solve for uv as a function of xy. That is, you're going to find the optic flow, u and v, for every pixel that tries to minimize this error. It's somewhat painful to try to implement systems that can